Hello everyone, welcome back. From this video, we would start our dynamic programming. So what is dynamic programming? So it's all about remembering what you have solved in past. The idea here is to do not compute the answer for the same states again and again. If you have already computed the answer for some particular state, then just simply return, restore the answer and use in the future. So I personally consider this Fibonacci series as the best and the easiest way to start the fundamentals of dynamic programming. So we all know the Fibonacci series starts from 0, then 1, and then the next term is the sum of two previous terms. So for example, these are two base cases, then other terms are the sum of previous two terms. So for example, this one is the sum of 0 and 1, then this 2 is the sum of previous two terms, 1 plus 1, which is equal to 2, then this 3, 2 plus 1, which is equal to 3, and so on. So this is an infinite series, and these two are base cases. And the prerequisite for a dynamic programming is recursion and backtracking. So how we can write a recursive function to find the nth Fibonacci series. So it's very simple. If f of n is representing the nth Fibonacci term, then what would be the recurrence relation? So f of n is equal to f of n minus 1. It's super simple. The sum of previous two terms plus f of n minus 2. Cool. So let's just quickly code this up. So here is my Sublime text editor. Here I will provide the input and we will get the corresponding output in this output.txt file. So let's take the input from the user and then I will simply print the nth Fibonacci number. So fib of n. So this fib is a recursive function. So int fib and then integer a n, and this function returns me the nth Fibonacci term. So the very first thing that we write is a base case. So if n is less than or equal to 1, or you can write it this way: if n is equal to 0, then return 0 because the 0th Fibonacci term is 0. If n is equal to 1, then I will simply return 1. So I can combine these two base cases and I can just simply write if n is less than or equal to 1, then just simply return n. Cool. Otherwise, what I will return the sum of previous two terms. So fib of n minus 1 plus fib of n minus 2. So let me just quickly test this for a few simple inputs. So let's say for 0, the expected output is 0. Let's say for 2, the expected output is 1 because 1 plus 1, which is equal to 2. Then let's say for 5 or maybe for 6, I guess the 6 Fibonacci series is 8. Fibonacci term is 8. You can also check from here. So n is equal to 0, n is equal to 1, 2, 3, 4, 5, and 6. Cool. So let me just quickly try run this recursive function for some particular value of n and analyze the recursive tree. So let's find the fifth Fibonacci number, that is n is equal to 5. Cool. So here I'm writing this Fibonacci function fib as f just for a simplicity. So f of 5, from the main function we have called this function f of fib of 5. Then it's not a base case. So fib of 4, then fib of 3, n minus 1 and n minus 2. Then from here, n minus 1 and n minus 2, fib of 3 and fib of 2. Similarly, fib of n minus 1, 2, and n minus 1 and n minus 2, 1. Cool. Then f of n minus 1 and n minus 2. Then similarly from here, f of 1, n minus 1 and n minus 2, f of 0, right? Similarly, f of 1, n minus 1 and f of 0. Cool. So then f of 1 and f of 0. So these are my base cases. These leaf nodes are representing the base case. So here the value of n is 1. So I will simply return 1 from here. That is, if n is less than or equal to 1, then return n. And from here, I will write 0. I will simply return 0 to the parent function. And f of 2 is the sum of previous two terms, that is f of 1 and f of 0. So I will simply return 1 plus 0, which is equal to 1 to the parent function. Then for this 3, I know the value of f of n minus 1. Then I will make a call for n minus 2. So this is a base case. So I will simply return 1 to the parent function. And here I will simply return the sum of these two terms, which is 1 plus 1 equal to 2. So I will return 2 to the parent function. Then from here, for f of 4, I know the value of f of n minus 1. So it's time to compute the value of f of n minus 2. So I will make a recursive call for f of 2. Then for this f of 2, I will make a call for f of 1. This is a base case. So we'll simply return 1 and n minus 2 base case. So return 0. Then return their sum to the parent function. Then I will return this these two values, sum of these two values, 2 plus 1, 3 to the parent function. Then for f of 5, I know the value of f of n minus 1, that is f of 4. So it's time to compute the value of f of n minus 2, that is f of 3. So I will make a recursive call for f of 3, not a base case, make a recursive call, not a base case, make a recursive call. So here, from here, it is a base case, so return 1. This is also a base case, return 1. Then, sorry, return 0, f of 0. Then from here, I will return the sum, 1 plus 1, which is equal to 1 plus 0, which is equal to 1. So I will return 1 to the parent function. And for f of 3, I know the value of f of n minus 1. So time to compute n minus 2. So base case, return 1. Then return their sum to the parent function, 1 plus 1, which is equal to 2. And for f of 5, I know the fib of n minus 1 and fib of n minus 2. So return their sum to the main function, which is 3 plus 2 is equal to 5. And here you can see the fifth Fibonacci term is 5. So I will simply return 5 to the main function, and this 5 will get printed. Cool. So what is the time complexity of this recursive solution? So isn't it like a complete binary tree? Almost complete binary tree. At every level, we are having 2 power something number of nodes. It is not exactly the complete binary tree, but when the value of n is large, so we can consider it is almost equivalent to the complete binary tree. Some numbers of nodes are missing, but those some numbers of nodes are constant and can be ignored. So that's why the time complexity is 2 power n. So when to use a dynamic programming? So here, if you observe this recursive tree, then you will find that we are computing the answer for some states again and again. That is, there is some overlapping states. For example, this f of 2. So this f of 2. So this subtree, we are calculating the f of 2 value again and again. Then for f of 3, you can see this subtree and this subtree are exactly same. So we are computing the same answers again and again. So that is where we use a dynamic programming. So it's all about remembering what you have solved in past. If you have already solved the answer for some state in past, then you don't need to solve the answer for the same state in the future. Just simply store the answer as use it. So this is the motivation why we need a dynamic programming. Now let me just quickly generalize all the things, how to write a dynamic programming solutions, and what are the two various different approaches to write a DP. So the very first step, let me write a steps here. So the first step is to form a state, and define a function, define a state f of x, comma y, comma z. So these are the variables, and they must be independent variable. These variables must be independent, because if there is something which is not independent, and let's say you can find the value of y, that is the value of y is equal to 2x. So you don't need to include the value of y in the parameters. You don't need to include this variable y in the parameters, because this y is dependent on x. So you can simply calculate the value of y inside the function, which is equal to 2x. You don't need to write it here. So make sure that these variables must be independent. And for example, how we have defined the value of f of n. So this was the state for a Fibonacci series, and I have defined in this way. This n is an independent variable, and this means nth Fibonacci term. F of n is representing the nth Fibonacci term. And for the same recurrence relation, for the same problem, you can write you can form a different states, and the same problem can be solved with the help of a different state. It's not necessary that for some problems you have only one state. You have to form the state in this way. It's not mandatory. It's totally up to you how you can form a state, but the way you form the state accordingly frame the recurrence relation. So which is the second step? The second step is to form a recurrence relation. So in the previous example, we have seen for the Fibonacci series, the value of f of n, it is equal to f of n minus 1 and plus f of n minus 2. This was the recurrence relation, right? And there is one terminology which is very important when we talk about the recurrence relation. It is optimal substructure. Substructure basically means a subproblem, that is a smaller version of the same problem. And here the term optimal means we should have the optimal number of terms, that is not extra, not more, not less, not more, not more. In this recurrence relation, we should have a optimal number of terms, not less, not more. Here I can also write 0 into f of n minus 3, but it's not making any sense, right? So ideally, we do not write any extra term, or we do not omit any term from this recurrence solution. So make sure to form this recurrence solution very carefully. And it totally depends on the state, how you have formed this state. The way you have defined this state, accordingly frame the recurrence solution. And the third step is to write a base case. So what is base case? So base case are the smallest version of the same problem, which is not actually the problem. I know the solution for these cases. So if I write in the terms of in this term, then these are not a problem. I know the solution for these problems, these subproblems. For example, the base case for Fibonacci series. What is the value of f of 0? Isn't it 0? And what is the value of f of 1? It is 1. So these are the two base cases. They are not the problems. I know the solution for these subproblems. And generally, we solve these base cases using pen and paper. And one more thing, there is no restrictions in the number of base cases. You can write any number of base cases in your recursive function. But one important thing here is that here we are accessing the previous two terms. That's why I have written two base cases. Because let's say if you have written only one base case, f of 0 is equal to 0, then what is the value of f of 1? Isn't it f of 0 plus f of n 1 minus 2, n minus 1 and n minus 2, so minus 1. And this thing is not possible. So I know I am accessing the previous two terms, n minus 1 and n minus 2. That's why it's important to write a two base case. The fourth and the final step, overlapping subproblem. Overlapping subproblem. So after writing a recursive function, just analyze your recursive function and draw a recursive tree for some examples. And if you find that there is some overlapping subproblems, that is, for some states we are computing the answers again and again, then simply store the answers for every state, and whenever you require the answer for some state, just simply check whether we have solved this state previously or not. And if you have already solved, then just simply return that answer. Don't need to compute the state again, answer for that state again, because it's totally waste of time and memory. So as we have seen in the recursive tree of a Fibonacci series, here we have overlapping substate. So what I will do, I will store the answer for each and every state and will use it in the future. So if there is an overlapping subproblem, that is, to resolve this, you can use, there is two methods basically. The first one is a top-down approach, which is recursion plus memorization. Recursion plus memorization. We write exactly the same recursive function and use a data structure to memorize or to store the answer for every state. Cool. So in this top-down approach, we start building the solution, big solution, right away by explaining how you build it from a smaller solution. So let me just quickly write it here. So we start building big solution basically right away by explaining how you build it from a smaller solution. Cool. So let me write a recursive, or basically let me just quickly memorize this recursive function. So here I will declare one data structure to store the answers for every state. And I know the answer for every state is of integer data type. That's why the data structure must be of integer data type. Cool. So let's say memo, and let me declare this memo array of some bigger size. So let me write a constant int. So int constant. Okay. So it's basically constant int n is equal to, let's say, 10 power 5. So 1 followed by 50, and then this n. Then first I will set all the values to -1. So for that you can use a memset function of C++, which takes the parameter, the base address of the array, and integer -1, and then the size of this entire array. Cool. Now all the elements, all the indices are having value -1. And why I have set this to a -1? Because I know -1 cannot be the answer for any state. So if there is a default value, then this means this is the first time we encounter this state, and I need to compute the answer for this state, because for the first time I have to compute the answer for this state. So what I can do, let me just quickly erase these two lines. So this is the base case. Then I will simply check if I have not computed this answer yet, this state yet. So if memo of n not equal to -1, what does it mean? It is not equal to its default value, then simply compute. It is not equal to its default value, then this means I already know the answer for this state, so I will simply return this answer. So return memo of n. Otherwise, I will compute the answer. Answer is equal to this thing, and then I will store this answer. So memo of n is equal to answer, and then I will return this answer, or you can say memo of n, whatever you want. Cool. So let me just quickly build this program again, and we got the same output 8. And what is the time complexity of this solution? So the time complexity of this solution, it is O of n, because there are only n different values of n from the initial value of n. And what is the auxiliary extra space? So here I have declared this array of size 10 power 5, but you don't need to declare of that big size. You just have to declare of size n plus 1. So here I'm writing the space complexity, auxiliary space complexity, as O of n. This O of n because of this memo array, and another O of n because of the recursive call stack. Here if you observe this recursive tree, then we are calling the function. So from this n, f of n, we are calling for n minus 1, n minus 2, n minus 3, and so on till 0 or till 1. So at any moment of time in our call stack, we would not have more than n functions. So that's why O of n for a call stack and another O of n for memo. So this is for memo, and this is for call stack. There is another way of writing a dynamic programming solution, which is a bottom-up manner. So this top-down is a recursive approach, and the bottom-up is an iterative approach to write a dynamic programming solution. And one very important thing, if there exists a top-down DP solution for some problem, then there must exist a bottom-up DP, and vice versa is also true. If you can write an iterative solution, then you can also write a recursive solution. Cool. So this is known as a bottom-up. So bottom-up DP. So this is also known as a tabulation, and the idea here is to start from the base cases, and from the help of the base cases start building the solution. So here we start with a small solution, and then we use the small solutions to build large solutions. So let me write a code that is an iterative approach. So also let me write iteration here, iterative approach. So let me just quickly clear all these things. So here what I can do, I can just simply take an integer n from the user, and then I will declare a vector or array of size n plus 1, because I need to access the nth Fibonacci term. So for that I required a nth index. Cool. So then what I can do, start from base case. So dp of 0 is equal to 0, and dp of 1 is equal to 1. These are my base cases, and then start from index 1, index 2, not 1, and go till n, and dp of I, it is equal to dp of I minus 1 plus I minus 2. So exactly the same thing, dp of n is equal to dp of n minus 1 plus f dp of n minus 2, the sum of previous two terms. One important thing here, I am incrementing the value of I, that is starting from the smaller values of I to the bigger values of I. That is, first I am building the smaller solution, and then with the help of a smaller solution I am building the larger solution. So before reaching to dp of I already know the answer for dp of I minus 1 and dp of I minus 2. And then I will simply print the value of dp of n, that is nth Fibonacci term. So cool, this is the expected output 8. And what is the time complexity of this solution? So here the time complexity is linear, O of n. We are using iteration, we're using a loop from 2 to n. So it's almost equal to n, and then the extra space that we are using is O of n because of this TP array. And here we got an advantage over the recursive solution, as we are not using a recursion. So that's why this O of n terms got eliminated from the space complexity in iterative solution. Here we do not have any extra space O of n for the call stack, as we are using iterations. And one more thing, also the time complexity is same in both the cases, the recursive and iterative, both the cases. But it's an belief that bottom-up DP is slightly faster than the top-down DP, as here uh, we are using the iterations, which causes less overhead for a CPU. So that's why it's believed to it's believed that the bottom-up solution is slightly faster than the top-down. So these are the steps for to write a dynamic programming solution. Let me just quickly summarize it once again. So the first step is to form a state, and make sure to always carefully form a state, because your recurrence relation is totally depends on the way you have formed this state. And the second step is to write a recurrence relation, then figure out the base case, which is the smallest possible case for which you already know the solution. Then the fourth step is to analyze the recursive tree, and if there is an overlapping subproblem, then just simply memorize the answers and use those answers in future. So let me just give you an homework problem. So if you observe one thing, then let me write a Fibonacci series again. So 0, 1, 1, then 2, 3, 5, 8, 13, and so on. So what we are doing in this DP array, so DP of I, it is equal to DP of I minus 1 and plus DP of I minus 2. So for every state, what we require, for every DP of I, we just only need two previous values. But in our DP array, what we are doing, so DP array, base case 0, 1, and let's say n is equal to 5, or maybe n is equal to 6. So n is equal to 6. So then what I am doing, DP of I. So DP of I is equal to DP of I minus 1 and plus DP of I minus 2. So it is 1, then 2, 3, 4, 2, 3, 5, and 8. So then I am printing DP of n. So that is this value. But if you have noticed here, I have stored all the values, all the previous values. But actually it is not required. To compute the DP of I, to compute DP of I, you just only need DP of I and I minus 1 and DP of I minus 2. But we are storing all the previous value. To compute DP of 6, you just only need DP of 5 and DP of 4. So why you are storing all these previous values? So what you can do, you can just solve this problem by using two variables a and b. Just only keep track of the previous two terms and keep on updating the previous term. Keep on updating the terms for the upcoming terms. So let me just give you an hint. So declare two variables a and b, and then find the value of c, which is equal to the sum of previous two terms a plus b, and then update the value of a and b, that is for the next upcoming term. So this is c. Then for c dash, so this gonna be the c dash, that is the next term for the next iteration, and this is the value of b dash, and this is the value of a dash. So update a and b accordingly. So how to update a and b? So first update the value of a, which is equal to b, and then update the value of b as c. So the current c will become b in the next iteration, and the current b will become a in the next iteration. So in this way, you can just simply eliminate this extra space and reduce it to a constant. And yeah, this is the solution. So try to implement it by your own. So this is all about the introduction to a dynamic programming. In future videos, we'll solve some problems. So thank you so much.